Okay, so today we're going to go through decision theory, and in the last class we talked a little bit about certainty equivalent wealth, and I actually thought we might start with a little bit of a refresher. I want you to assume, we'll do a little problem, that our person has a cube root utility function, and that they've got, I'm just going to make this up right now, a 40% chance of having a wealth of 0 and a 50% chance of having a wealth of 8 and a 10% chance of having a wealth of 27. 40% 0, 50% 8, 10% 27. And I want to know what is the certainty equivalent wealth of that lottery to them. You can use any tool you want.
I'm sorry, I just opened my notes.
Okay? 40% 0, 50% 8, 10% 27. People have results? Where is it?
Yeah.
All right, so let's go through this problem together. And for those who are a little bit late, we have a situation in which there's a 40% chance of getting 0 in a lottery, a 50% chance of getting 8, and a 10% chance of getting 27. And the person who's evaluating the situation has a cube root utility function. So I'm just going to start doing it as a spreadsheet problem, and then we can use a little fancier methods. But I've written down the probabilities here. Can you all see this, or is it too small? I'll make it bigger. Okay. I've written down the outcomes in column B. In column C, hopefully you can see I'm just using a formula where I'm taking the cube root, and that just gets dragged down to here, and I picked numbers that I knew had easy cube roots. Our weighted utility is the product of the probability times the utility, C2 times A2, and that drags down. And then we add them all up, and we get an expected utility of 1.1. Okay? That's the sum of these three numbers. And then to convert expected utility back into certainty equivalent wealth, we ask the question, what amount of money, if held with certainty, would yield a utility of 1.1? And for a cube root utility function, this is easy. The inverse of a cube root is simply to take the cube. And so if I take 1.1 cubed, which I'm doing here, I get 1.331. And so we see that this person, in some sense, is pretty darn risk averse. That's what we get. So, any questions on that? All right, let's do it in R and Mathematica, and we'll see how that works out. Let's start with Mathematica. And we'll make a little new notebook here. Okay. And what we'll do is we will, all right, let's do it the right way. Let's create a distribution that represents the situation. We have an empirical distribution, which is very flexible. And there's a 40% chance, a 50% chance, and a 10% chance. And the respective outcomes are 0, 8, and 27. Yes? Okay. And so what I want to do is I then want to transform this distribution by the utility function. So I'm going to make a transformed distribution where it's x to the 1/3 power, where x is distributed according to this underlying distribution. Comma, close it up. Everyone see what I've done? So we start off with what are the actual outcomes, and I'm now going to transform it and not look at the actual outcomes, but to look at the utility of each of the outcomes by taking the cube root. And to calculate the expected utility, I'm simply going to wrap an expectation, or I can wrap a mean around this. But let's do it with this expectation. I can say, what's the expectation of, name your thing, z, where z is distributed according to the utility function, according to the utility distribution. Does that make sense? And if I do that, I get 1.3, which is not the answer that I got here, but it is the answer when I did it by pencil and paper over here. So now we need to figure out, where did I mess up? First of all, let's make sure I have the numbers the same. 40, 50, 10. 50, 40, 10. Which did I say? I said 40, 50, 10, didn't I? All right, so if I do this, and one of the nice things about spreadsheets is it all updates, and now I get an answer that looks exactly like the answer that I got when I did it by pencil and paper. And so instead of stressing out quietly to myself about how did I screw it up when I did it by pencil and paper, I now realize that I just screwed it up when I did the spreadsheet. So this is the correct answer. That we did it, the math was right, it's just that I had the numbers wrong. All right, and so we now have the expected utility, right? And so now all I have to do is to take this and cube it. And that will get me the certainty equivalent wealth. Okay? So what I'm doing is I'm taking a utility function here, and at the very end I'm inverting that function. Okay? And so one way of thinking about this is, let's actually plot what a cube root function looks like over the relevant domain as x goes from, let's say, 0 to 27. And so 40% of the time my utility is here at 0, and 50% of the time it's up here at 2, and 10% of the time it's up here at, well, my outcome is at 27 and my utility is at 3. And so there's some utility here which is actually 1.3, which is the weighted mean of those outcomes. And so what I'm now asking is, let's suppose I'm over here. I know my utility is 1.3. If I go backwards here, where will I end up? If I start with utility of 1.3, what level of wealth, if held with certainty, would have generated that utility? And it turns out the answer is 2.197, which is exactly where I've managed to place my cursor. Does that make sense? Okay. So let's do it in R. Oh, by the way, I went through kind of an elaborate process here. In this simple case, there is no real reason to go through such an elaborate process. If you actually asked me to find this answer quickly, I would probably do something like this. I would set up the probability vector, and I would dot that onto a mapping of the cube root function. Or here, I'd do something even easier. I'd do 0, 8, 27, and I would exploit the vector processing of Mathematica to do that. And that would get me that number, and then I just take that and cube it. Okay? So that is a more concise way to do it in this somewhat simple case. If you have more complicated utility functions, you might want to use this. And the reason that I happen to like this is it sort of corresponds a little more mathematically to what's going on. But any way you like. Okay? This is, however, going to help us with the R version, because as you know, R doesn't really have this notion of an empirical distribution. It has an empirical cumulative distribution function, but that's not really what we need. So let's go to our R, and we'll go generate an R console here. Let's just generate a new little script file. And since we're in class now and not me just working in my office by myself, we'll increase the font size to a very legible 18. And so you guys tell me what I should write. What should I write?
Well, I guess we could do it like the last example you did in Mathematica.
Which
So-
I'll even be so nice as to kind of try to show you there, all right?
So I think we do C parenthesis 0.4 comma 0.5 comma 0.1, and then I think it's the percent star percent,
That's what it is.
and then the C parenthesis 0, 8, 27.
Okay.
And then and then caret or exponentiate that to the 1/3. And I guess
And I
that should
think
give
I
us-
need these parentheses, otherwise I think I have an order of operations problem.
and so that should give us 1.3.
Well, let's see if that does. And lo and behold, it does. And now what could I do?
And then you could wrap the whole thing in parentheses and raise it to the 3rd power.
Okay. And that should do it. Okay? So that's the R code that you need to find certainty equivalent wealth. And so once like a lot of things in the world, often the hard part is just getting it in this form. That is, life doesn't usually present itself as here is a lottery of the following situations. Rather, you've got some scenario that the law creates, and you'll see in the problem set that I've generated some of those scenarios, and it's a word problem. You've got to translate it from what's being described to something that you could represent more mathematically. But once you've got it as a lottery, really the code for figuring out certainty equivalent wealth is not too bad. Okay? All right. As you might recall, last time, and I think I have to recompile, we were talking about, though, an alternative method which had some virtues called spectral measures, which I wish, as I say sometimes, it should be called expected quantiles, but it's not. All right. So we were about here. Okay. And I think I mentioned that the idea is that you sort the outcomes from the worst case to the best case. And then you either increase the probability relative to what it really is for the worse outcomes, and you decrease the probability relative to what it really is for the better outcomes. So your total weights, just like your total probabilities have to add up to 1, your total weights have to add up to 1, but you're putting a thumb on the bad results. And you could just, as I said, you can think of this as sort of an obsessive compulsive person who all they can think about is the bad stuff. And in fact, there are subspecies of spectral measures that have their own names, of which probably the most famous is called expected shortfall. And expected shortfall is you usually take the worst 5% or maybe the worst 10% of the possible outcomes, and you just look at those. That's all you look at, and you treat those equally, and you just take a weighted average of what is the weighted average of, or what is the average of the worst 10% outcomes. And sometimes people use that as a way of evaluating how risky an investment is. Personally, I don't think that's a very good measure, because you could have two lotteries or two investments. Yeah, they both had bad bottom 10%, but they could have very different upsides. And expected shortfall isn't going to really tell you which of those is better. So sometimes people combine expected shortfall with the mean to try to get a handle on what the investment looks like, with expected shortfall kind of being a measure of the bad side and mean being a measure of how good it is on average. Okay. And that is, expected shortfall is a spectral measure. It's kind of one in which I can show you the weighting function. The weighting function looks like this. It's plot if x is less than 0.1, let's say, then it is 10, and if it's otherwise it's 0, and let x go from 0 to 1, and that's the weighting function, okay? And remember that the area under the weighting curve for a continuous value function has to be 1, otherwise the weights don't add up right. So that's what it looks like, okay? Where you're really having a heavy emphasis on the bad side. All right, so let's do a practice spectral measure. And here, let's keep those same outcomes, where there's a 40% chance of 0, a 50% chance of an 8, and a 10% chance of a 27. And I want you to assume that the weighting function, where's that little, here's what your weighting function looks like. It looks like this. It's basically a triangle. And you can assure yourself that the area under the triangle is 1, because remember, the area of a triangle is height times width times 1/2, back from whatever grade. So that's 1. So that is it also satisfies all the other criteria. It's never negative, and it's never going up. So this is an admissible spectrum. So what I'd like to know is, what is the spectral measure of a scenario in which this is the weighting function and the outcomes are as stated. Okay? And you can either, let's spend a few minutes doing it on your own. I think you're going to be happier doing this in Mathematica than R, but your pick. And I'll give you should I give you a hint? No. I'll let you suffer. Actually, I will give you a hint. It's such an evil hint. Trapezoids.
Discuss.
Where's the web browser? There's a lot of information on trapezoids here. Who knew? Anyone have an answer?
What are we looking for? The expectation
I'm
value?
looking for the spectral measure.
Oh.
That is, essentially, how would a person who had this sort of weighting function, how would they value that lottery, where there's a 40% chance of 0, a 50% chance of 8, and a 10% chance of 27? And I'll give you one thing which can test your answer, which is the expected value of that lottery is what? 0.5, 0.1, dotted with 0, 8, 27. The expected value is 6.7. That's what someone who was risk neutral, who had a flat weighting, would say. So it should be somewhere between 6.7 and the worst case of 0. So if you're getting a number of 9, you know that's wrong. And if you're getting -3, you know that's wrong. As long as they're risk averse, it can't be greater than the mean. But that's not as good a hint as my trapezoids.
0.36.
I don't know the answer, so that might be right. I want to let me calculate the answer. Let's do it together. All right? All right, so here's one way to think about it. There is a 40% chance that it's going to be 0. So what we want to do is to accord the weight on 0 should be equal to the area of this trapezoid here. And that way, the weight we place on 8 should be equal to the area of this trapezoid here, up to 0.9. And the weight on 27 should be equal to the weight on this. It's a degenerate trapezoid, it's a triangle. The weight here. Does that make sense? And so we can actually do that, and I guess remembering vaguely that the area of a trapezoid is the mean of the length of the parallel sides times the length of the perpendicular side. It's the area of that first trapezoid is 0.4 times the mean of 1.2 and 2. 1.2 is this point here because it's 2 minus 2 times 0.4. Okay? So And we're going to multiply that by the outcome, which is 0. So all that is for naught because it's going to turn into 0 at the end. Plus, we're going to take this trapezoid, which has a distance of 0.5, and we're going to take the mean of 1.2, and let's see, at 0.9, this height is 0.2. And then we're going to take the mean, or I'm sorry, the next area is 0.1 times the mean of 0.2 and 0, and we're going to, we need to multiply this by 8 and this by 27. And so what we've done is to weight each of the results by their corresponding trapezoid. And when we do that, I get 3.07. Okay? That works fine, although it's a little bit clunky, if you have the nice line here where you can use a trapezoid formula. Okay? In general, it might not be a line, and then you have to resort to some calculus. Okay? So this, I think, is our first use of calculus here, but it's not so bad. We're just integrating this area multiplied by these values. Okay? So let's actually do an integral. Let's integrate. And it's something times 2 minus 2x. What's that? And as x goes, let's actually, can I use q? I'm going to use q instead of x. As q goes from 0 to 1. What's that something? Well, if it's a piecewise function, isn't it? If q is between 0 and 0.4, then we want to multiply by 0, because that's the value of that's the utility in those quantiles. If q is between 0.4 and 0.9, then we want to multiply by 8. And if q is between 0.9 and 1, then we want to multiply by 27. So I've created a function here that expresses the value as a function of the quantile. And I'm simply multiplying that by the weights, and I'm going to integrate, and I'm going to be very sad if this isn't 3.07.
You gotta fix that comma. The key, your cursor's almost. It says 0.4 greater than or less than.
Thank you. And we need to be consistent here. I don't think Mathematica is going to object, but I'll object. All right, so that's one way to do it. The other way to do it, the final way in Mathematica to do it, is to say, look, what we're really calculating is we have a quantile function for every, which is the inverse CDF function. For every quantile, I can tell you what the result is. And the simplest way to think about this is good old GPAs. Students are really familiar with GPAs. So if I say, what is the 90th quantile of the University of Houston Law Center grade point function? It's what, about 3.5, 3.45? That is, 90% of students have a GPA under 3.5. Okay? If I ask you what's the 25th quantile of the University of Houston's GPA function, it's 2.7, 2.75, something like that. Okay, does that make sense? That's what a quantile function is. And so what I'm really doing is calculating the expected quantile with the quantile weighted according to the weighting function. That is, the quantile is an outcome. You got a 2.75 GPA, you got a 3.4 GPA. But we're going to weight that according to the fact that you're very stressed out that you might have a bad GPA. So we'll take the expectation of the quantile of this empirical distribution with respect to Q, and we'll let Q be distributed according to, let's see, how could we represent 2 minus 2Q? Why, I know. Let's look at what the probability density function is of a beta distribution whose first parameter is 1 and whose second parameter is 2. And you can see why, my goodness, it's exactly what I wanted. Who would have thought? It's 2 minus 2Q, or 2 times 1 minus Q. So I'm going to write this, instead of writing this the simple way as 2 minus 2Q, I'm of course going to write this as a distribution. Okay? And so what I now have is, let's look at this expression again. Look, this is my outcome distribution. This is what outcomes I might get with the associated probabilities. This is a distribution function whose PDF represents the weights I attach to that. And the only restriction on this distribution function is, again, remember, it has to always be going down, and it has to lie only on the interval 0 to 1, because if it doesn't lie on the interval 0 to 1, and it lies, for example, on the interval 0 to 2, then it won't add up to 0, it won't add up to 1 on our, as Q goes from 0 to 1. And I want to take the expectation of that. And when I do that, bless us all, it is 3.07. Okay? So, these are 3 different ways of determining the spectral measure. The trapezoid measure, although it has pedagogic value, I wouldn't recommend that you use it in the real world because, first of all, this is a little bit cumbersome. Not that this is so easy, but this is a little cumbersome. And also, it's only an approximation where this is curved. So, I would much rather see you do it either this way, or frankly, this is the best way to do it. Okay? Using the expectation. There are times I can write some crazy function here where Mathematica can't do this symbolically, and there's the numerical expectation where it says, I don't know how to do this in the fancy way, let me make an estimate. And it's the same answer. Okay. Any questions on that? All right, so let's do the same thing in R. And so let's turn to, I actually wrote up, I think, a better version of this. Numeric integration in R. Okay, we haven't done any calculus in R yet. Okay. All right, so here's the lottery that I asked you to do. 20% chance of being negative 5,000, 50% chance of 1,000, 25% chance of the result being 9,000, 5% chance of the result being 18,000. Assume that the weighting function is the PDF of a beta distribution with a first parameter 1 and a second parameter 3. So before I make you do this in R, as a fun exercise, do this in Mathematica first, based on what I already told you. That should be a doable proposition. And if you don't have your laptop with you, write down what you would write. And maybe I would be kind enough to kind of leave that stuck on the board there. And I'll move it over here so that you can actually see both things at the same time.
It should be negative, right?
I don't know what the answer is. But actually, I think I do know what the answer is, and I think it is negative.
It's distributions. Three dots and then you write distribution after it. Vertical though.
What answers do we have?
Negative 1,710.8.
That sounds pretty good. Let's see what my answer is. All right, expectation of the quantile of this little lottery that I just defined with respect to Q, but Q is distributed according to the PDF of a beta distribution with a first parameter 1 and a second parameter of 3. And by the way, you can see what that's what this looks like. That's this here. So it's even more heavily emphasizing the bad stuff than our linear relationship did. There's more stuff here. So let's actually do this and look at that. Negative 1,710.88. Okay? All right, so now we've done it. We know what the right answer is. We kind of conceptually know how to do it. How do we do this in R? All right. Step 1, define your quantile function. Okay? So here, remember how I sort of did it as a piecewise function in Mathematica? This is how one way to do a piecewise function in R, where you say it's negative 5,000, and we're going to multiply that by this basically Boolean expression, true-false expression. If Q is greater than or equal to 0 and it's less than 0.2, when you evaluate this, if this is true, R will say 1. True has a value of 1 in R, and you're going to exploit that as a way of making the code fairly concise. If Q is between 0.2 and 0.7, this is 1, and so we'll add 1,000. We'll add 1,000. Similarly for 9,000 and for 18,000. Okay, so I've defined a function G, function of Q, that basically is the outcome of our lottery as a function of the quantile of the result. Okay? That's step 1. Step 2, define your weighting function. I can't just say beta distribution 1, 2. R doesn't know what to do with that. How do I know that that's the PDF of a beta distribution 1, 2? If I'm just using R, I'm going to be hard pressed to it. So either I'm going to have to tell you what it is, or you're going to have to switch over to something like Mathematica, which is able to do these things symbolically, and that's how you're going to find it out. Okay, so that's a little weakness of R. There are workarounds and there are packages which link to various things, but really, for you guys, it's going to be much simpler just to run Mathematica. Or I'll tell you, here's the weighting function. Create a product, F. It's G of Q times W times Q. Okay? So we've got the value as a function of the quantile times the weight according to that quantile. Step 4, integrate that function, F, as F goes from 0 to 1. Okay? And lo and behold, we get negative 1710.882, and it's actually going to tell us, because it's doing it numerically, it's going to tell us, I'm not so sure exactly what it is, because it's doing little trapezoids too, or fancier algorithms for doing integration, and so it's going to tell us that's my error bar. It's not worse than that. Okay? And I guess those are the steps. That was it. So that's how you do expected quantiles in R. It's not as pretty as Mathematica, but you can get the job done. And so that's how you do it. All right. No, you don't need to see that. What happened to decision theory. Let's submit it again. Right, we need to go to order distributions, don't we? All right. This is just a discussion of exactly the same thing. Properties of spectral measures. Here's some nice things about spectral measures. Okay? And you might be thinking, why would you use this? It seems kind of cumbersome. But it has these nice properties where if I double all the numbers in my problem set, instead of 0, 8, 27, it turns into 0, 16, 54. It just doubles the spectral measure. That is, it doesn't care what units you're using. Okay? Whereas, so if I'm using dollars or hundreds of dollars, it doesn't care. And that's actually a potential issue with certainty equivalent wealth, where it's not always the case that if I double all the numbers, I get double the result. So it's also, and by the way, if you want to be fancy, you say that's a positive homogeneity. It has the property of positive homogeneity. Okay, so it also has translation invariance, meaning that if I add 5 to each of the numbers, I say the worst outcome is 5, the next worst outcome is 13, the next worst outcome is 32, then I just add 5 to the spectral measure to get the result. Okay, so it doesn't matter sort of where you set your 0 point, the answer always comes out the same. And that is definitely not true of certainty equivalent wealth measures, but it is true of spectral measures, and to me that reflects reality. That is, if I'm evaluating a risk and you tell me I'm going to get $5 more in every single instance, I would think I would say, well, now the lottery is worth $5 more to me. And so it has that virtue. And of course, since it has positive homogeneity and translation variance, that also means if I quadruple all the outcomes and add 7 to it, to calculate the new spectral measure, I can just quadruple the old spectral measure and add 7 to it. Those affine transformations work as well. All right, we talked about expected shortfall, order distributions. Okay, so here's another way of thinking about risk, and this again, it's sort of a cousin of spectral measures. Supposing I have my outcome, and what I always think of is, supposing I rolled my dice twice, what is the distribution of the lowest roll? Okay? We know that if I roll a fair die once, the distribution of the outcome is going to be equal, right? If it's a fair die. But if I roll it twice and my score is the lowest outcome, you might ask, what is the resulting distribution? And actually, Mathematica is very nice at dealing with this. Let's go to Mathematica here, and we're going to say we have a discrete uniform distribution, and the possible outcomes are 1 to 6. Okay? And I can ask it to do a discrete plot of the PDF of this as x goes from 1 to 6, and it gives me a very boring result, right? It just shows me that everything's equal. All right, but I've shown you various transforms of distributions before. I've said, look, you can censor a distribution. We haven't talked too much about truncated distributions, but you can truncate a distribution. You can transform a distribution, right, by saying take the result and square it and add 7. We've got one more transform to talk about, and that's an order distribution. And an order distribution is exactly what I'm talking about. It says run it n times and figure out what is the kth worst outcome. So I'm going to say, what is the order distribution? Okay, and since I haven't used this in the past week, I'm going to look it up. Dist nk. Okay, so I'm going to say of a discrete uniform distribution on the interval 1 to 6, n is the number of rolls, 2. Which outcome am I interested in at the moment? I'm interested in the first worst outcome. If I evaluate that, it just tells me, okay, Chandler, you've got an order distribution on a discrete uniform distribution twice, you want the worst outcome. But if I now say calculate the PDF of that, it actually does it. Okay? And it comes up with some yucky thing, but I can say discrete plot it. Okay? As x goes from 1 to 6, right, the lowest still can't be lower than 1, and it can't be bigger than 6. And so, it kind of looks like our friend a line. I guess it isn't actually a line. Hang on, 1 second here. Is it a line? Let's do a full simplify on this and see if it turns into a line. That's the equation of a line, isn't it? All right, so it is a line. And so what does this, by the way, kind of look like? Where have we seen something that looks like a line before?
Weighting function.
What?
Weighting function.
And wasn't when I did the PDF of the beta distribution where the first parameter was 1 and the second parameter was 2, right? Well, let's look at the PDF of a beta distribution on 1, 2 of Q, and let's plot this as Q goes from 0 to 1, and it's a line, okay? Now, could that just be a coincidence that this number is 2 and that number is 2? Well, let's see. Supposing I want to know I roll the dice 3 times, and I want to know what is the distribution of the worst possible outcome if I roll it 3 times. Kind of looks curvy, doesn't it? And what does this look like? It kind of looks curvy. Now, is this a proof? No, of course it's not a proof. All right, let's do 5 times. It looks like a curve that's going down fast. And let's do this. And it is, okay? And if we wanted to spend more time, you can actually prove that one way of thinking about a beta distribution on 1,5 is it is how a person who had 5 rolls and picked the worst one, it's the same thing. And so an order distribution is in some sense, I don't know if it's simpler or it's harder, but it's another way of thinking about and analyzing risk, and it kind of motivates the idea of using a beta distribution. This is a unique property of the beta distribution. Other distributions will not do this, but there's sort of this marvelous property of the beta distribution that it emulates this situation of an order distribution. By the way, what if I want to know the distribution of the second worst roll? Okay? It looks like that. And is that an admissible risk spectrum? It isn't, right? Because it goes up. Okay? I wonder what this looks like. It kind of has the same shape, doesn't it? So you can get a sense here as to the relationship between these two things. By the way, here's something interesting. What if I ask you, what's the distribution if you roll the dice 1.7 times? Well, you can't do that, right? But you could think of the order distribution as a special case of this. And it's just kind of, I don't know what to make of this fact, but it's kind of interesting, I think, to think about rolling dice fractional times. But anyway, that's a distraction. In any event, you can therefore model outcomes. Let's actually model. Let's do this problem here. Let's do our old problem here. Okay, we've got our lottery represented by an empirical distribution. So let's calculate what is the order distribution. I don't know if Mathematica can do this. We're about to find out. Of our lottery, 2 rolls of our lottery, how many rolls do we have up here? We had 3 rolls. Let's do a 3 roll. We want the worst outcome. And I want the mean result of that. Ooh. That's very close, isn't it? 1710.87 versus negative 1710.88. And I'm just the kind of person who will obsess about why it is 0.01 off. But I have learned to sublimate my obsessions during class time. So we will not pursue that at the moment. But you can see certainly that there appears to be some close relationship between the two. Okay? So if you don't have a calculuser handy, you can actually just simulate the spectral measures by just sort of doing this, take 2 rolls and pick the worst and just keep doing it and finding out what's the mean. Okay?
Sorry, on the very last, on the last one you did with the lottery, that was the so you're getting 3 chances at the lottery. Okay, and you're taking the worst outcome of the 3 chances. Okay.
Mm-hmm.
Okay.
And I'll tell you the other virtue of order distributions. Okay, if I go up someone and say, you know what, your spectral measure in thinking about risk is the PDF of a beta distribution whose first parameter is 1 and the second parameter is 3. Many people, perhaps most, would give you a blank stare. Okay. Whereas if I tell you, you know, you are so risk averse that the way you think about things is you think about 3 things that could possibly happen and you always pick the worst one. Okay? That's a way of discussing a client, for example's degree of risk aversion. Okay? And so it's just a way of conversing about it. That's another reason I like order distributions. All right, so here are some problems that you might want to practice on. And when you're done practicing those, there's a problem set which is very similar to these. Okay, and that's what's due next week. So, those are 3 methods of evaluating risk: certainty, equivalent wealth, spectral measures, order distributions. And we're now in a position to go back to this problem. Remember this problem from yesterday? And I made enough that oh wait, this is the wrong one. I made enough so that we should be able to do it again today. Can you pass those down? And what I want to know is, what should a person who uses has a spectral has an order distribution? They use that 2 rolls theory. Okay. When they see a lottery, they think, what's the worst of the 2 outcomes? I want to know what they should do in this setting. Now I'm going to walk. I'm not going to make you do this. Okay. So, let's look at our lottery. Remember, we go to the bottom first in these decision trees. And we say, okay, how are they going to value that node 7? That's a little hard to see, but there it is. So, there's a 50% chance of them getting a 1, and a 50% chance of them getting a 15. So let's figure out the spectral measure here, or the order distribution. Let's actually create this. This is the node 7 lottery, and that is the same thing as an empirical distribution, where the outcomes are 50-50, or the probabilities are 50-50, and the outcomes are 1 and 15. Okay? And now what I want to know is, what is the mean of an order distribution of the node 7 lottery with 2 rolls, and I want the worst roll. And it's 4.5. Okay? So, what do we do then? What we do is we say our person is not going to pick the route from 5 to 7, because the route from 5 to 7 they value as a 4.5. Instead, they're going to pick, and I guess I have to erase it from yesterday where we were just using a risk neutral person, they're going to choose to go to 6. Yes? Yes. Okay. So now let's make our way back up to node 2. Node 2 is also a lottery, and now there's a 50% chance of them getting a 4 and a 50% chance of their getting a 6. Okay? And without doing any math, which would they prefer when they're sitting at node 1? Would they prefer to go to node 2 and enter this lottery, or would they prefer to go to node 3 and get 5 with certainty? You shouldn't have to do any math. You should just be able to say immediately,
This is a risk-averse person?
this is a risk-averse person. Remember, they look at 2 possibilities,
Yep.
and all they can think about is the worst case.
So 5. They choose 5.
All right, because if they're risk-averse, then the result again is less than the mean. And the mean of 4 and 6 is 5, so without doing any math, we know that they value node 2 at something less than 5, and therefore they should be choosing to go from 1 to 3. Okay? Make sense? All right, that's how we solve that. Now I need to make it a little more challenging. We now have a person, same scenario, but instead of using an order distribution where they take the worst of 2, they actually are a spectral measure kind of person, and their spectral measure it happens to be the PDF of a beta distribution of 1 and 1.25. Okay, so let's see what they choose to do now. All right, we have our node 7 lottery. What I want is the expected quantile of the node 7 lottery with respect to Q, with Q being based on a beta distribution with parameters 1 and 1.25, and let's see what that is. That is 6.88. And so now, if our person is sitting at node 5, what do they want to do? Do they want to go to node 6, or do they want to go to node 7?
Node 7.
They want to go to node 7 because they value that at 6.88. Okay. So now we have to move up to node 2. And here's what they're saying at node 2. At node 2, here's what they're not saying. They are not saying, I have a 50% chance of getting a 4 and a 50% chance of getting a 6.88. You can only use that 6.88 to determine whether they want to go from 5 to 7 or from 5 to 6. Instead, what they're saying is, I'm actually in a setting where I have a 50% chance of a 4, if nature puts me to node 4, a 25% chance of being at node 8, in which case I get a 1, and a 25% chance of being at node 15. This is called a compound lottery, and what I just did is to flatten the compound lottery. In other words, you're going through 2 lotteries here. The first lottery determines whether you go to node 4 or node 7, and if you go to node 7, the second lottery determines whether you go to node 8 or node 9. And so instead I want to turn that into a triple lottery, basically, in which, or not a single lottery with 3 branches, in which there's a 50% chance of going to 4, a 25% chance of going to 8, and a 25% chance of going to 9. Does everyone see that? All right, so let's look at this. We have a compound lottery. I'll call this the node 2 lottery. Node 2 lottery. And that is equal to an empirical distribution with probability 0.5, 0.25, and 0.25. The outcomes are 4, 1, and 15. That's fine. And now again, what I want to do is I want to calculate the expectation of the quantile function of the node 2 lottery. with respect to Q, with Q being distributed according to a beta distribution whose first parameter is 1 and whose second parameter is 1.25. And that is 5.038. And so, if I'm sitting at node 1, where do I want to go? Node 2 or node 3?
Barely, node 2.
Barely node 2. Okay. And if I change this number 1.25 to 1.28, we would be pushed over the line. Okay? And so, that's decision theory, and that's as hard as it gets in this class for decision theory, where you basically have the potential for a compound lottery. And what you have to do when you have a compound lottery, when you have two nature nodes that have been rendered next to each other, is you want to flatten it into a single lottery with more branches. Claro? Okay. And that's okay. So here's a by the way. By the way, we're not studying game theory in this course. However, you can think of decision theory as a special case of game theory. It's a simpler special case of game theory. In game theory,
Was game theory on the syllabus?
no.
Okay.
It's on the second page, but things we aren't going to do.
Yes. So it was all right. But just so you know, one way of thinking about game theory is instead of each node having one payoff, each node has, in a two-player game, two payoffs. The player, when you reach this outcome, it's the outcome to the first player and the outcome to the second player. And instead of what happens at each node is either owned by a player, player 1 or player 2, or it's owned by nature, as it is in some of these nodes. That's the chance nodes. They're lottery nodes. Okay? And so if the node is owned by player 1 uses the outcomes to them to figure out which direction to move. Whereas if the node is owned by player 2, then you use the outcomes to player 2 to determine which node you go to, which gets lopped off. And so there's more to game theory than that, but simple game theory with what's called perfect information it's very similar to how we look at decision theory. And so decision theory is just game theory with one player. All right, so now we've learned everything about game theory. We've learned decision theory. Let me tell you where we're heading. Because I did fiddle with the syllabus a bit.
Quick question.
Mhm.
Do you have answers for the problems? Like, not the problem set, but the problems
Problem
in decision?
9 or 10?
Oh, not
The
the
new
problem
ones
set,
you
like
just
the
gave one
problems you just
example.
gave us.
Oh.
Example problems.
So like we can be like, oh,
So we
okay,
can
this thing.
see.
That's a good idea.
Yeah.
No, I don't think I have them. I'm feeling like I am good enough that I can calculate these. I think I can answer my own questions, which is not always the case. So let me try to do that over the next day or so. Do you want me to post the answer so you can check your work? Would that
Yes,
be-
please.
That'd be great.
Thanks.
Okay. All right, I will try to post the answers to my stupid problems. Okay, I hope I didn't make them too hard. I decided that you really should come out of here knowing a little more about databases than you do, and also we keep kind of using them in class. I keep kind of saying, oh, we're going to use dplyr, okay? And so I think an excursion into R's treatment of databases would be a good thing. So that's where we're headed for the next 2 days. Originally we were going to have a guest speaker here, and we still are. It's just that the person doesn't know it. It's going to be Hadley Wickham's going to be appearing in class through YouTube. So he's the guy who designs a lot of R packages, sort of Mr. R, or I guess he's Mr. R. And so we're going to be watching some stuff of his. And then next Wednesday, we're actually going to use what we've learned to study one of my favorite things, which is healthcare.gov, the Federal Exchange for Purchasing Individual Insurance Policies, which, by the way, should...
Is it working?
Well, that's the question. On November 15th, it should reopen with new plan choices. And so, if they're doing their
No
job,
way that's gonna work right on the first day.
you think it might, huh?
No way.
No, he's betting it's not.
They
I thought
have...
they were gonna do 2 times in a row.
They have
You're right.
the data for all of the plans in a big file.
Wow.
And I'm hoping that, well, this is the shop exchanges, which are these, but here are the individual.
It's state by state, right?
It's more than state by state. It is every single plan that's sold on the federally facilitated exchanges. So it's like 28 states or something. And there are 78,000 plans in there, and they have 128 pieces of data on each plan. So it's a significant database. It's not, there are now databases that have like 1 trillion entries in them, and we're not going to tackle that. That's a whole different order of computing. But it's enough to make life interesting, okay? And so I want to show you how to work with data in R, mostly using dplyr. Okay? So that's going to be our goal. And because the more I thought about it, the more I thought, you know what? What are they really going to do when they're out there? They're going to have lots of data. They need to know how to fiddle with it. And so that's what you got to do. For the homework, you'll see it's about lawsuit settlement. And yes, you think lawsuits are interesting. Lawsuits are really just lotteries, okay? With the probabilities determined by you guys. And so you're going to use the skills that we've developed here to advise your clients on what settlements are appropriate. And then in one, I have you be a mediator and basically try to say, this case could settle anywhere in the following ranges. Okay? So I will be gracious and let you out, 6 minutes early. Okay? And I'll stop the little recorder. Stop.